Let's begin by comparing high-level C program, low-level assembly program, and machine binary code side by side. In high level, this is a very simple function that takes two integer numbers, adds them together, and returns the result. On the right-hand side, we have a 32-bit x86 assembly program. We have a label sum, which is the function name, followed by the 6 assembly instructions. Each line is a single assembly instruction. So the first machine instruction is push L EBP register. Anything beginning with the percentage symbol is a register name. The second instruction is move L ESP register EBP register. The last instruction is simply a return instruction. The final binary machine code is simply a sequence of bytes or bits that encode the individual assembly instruction from top to bottom. For example, the first instruction push L EBP register instruction is encoded into a single byte hex 55. The second instruction move L ESP register EBP register is encoded into 2 bytes hex 89 and hex echo 5. This one-on-one mapping and encoding simply follows the micro-formatting rule specified in x86 ISA document. Here we summarize observations from assembly code. First, the machine binary code is a sequence of bytes or bits encoding a series of assembly instructions. This process is known as assembling. The second, each machine instruction performs only a very elementary operation, such as adding 2 numbers stored in registers, transferring data between memory and register, or conditionally branching to the instruction address. Third, the format and behavior of assembly code is defined by ISA specification. Next, the assembly code contains lots of hardware information such as machine instructions, registers, and memory spaces, etc. Next, the instruction length and format varies, in this case, from 1 to 17 bytes in x86, because x86 is a CISC type machine. We will talk about CISC versus RISC a little later. There are 3 basic operations of machine instructions. The first category is arithmetic and logical operation, also known as ALU operation. And the second category of machine instruction is data movement or memory operation. The third category is control flow operation. All assembly instructions are under one of these 3 categories. Here's an example. The first category, the ALU instructions, perform arithmetic or logical operations on register or memory data. One example is add L parenthesis EDX register and EAX register. The second category of machine instruction moves or transfers data between memory and register, that is, loading data from memory into register or storing register data into memory. An example is move L 8 parenthesis EDX register and EAX register. The third category is to change the execution flow, that is, we jump to different location, unconditionally or conditionally. One example is jump L1 label. This is assembly programmer's view of system. If you look at the diagram, CPU and memory subsystem exchange the memory address and data or instruction. CPU requests the instruction or data by issuing a memory address to memory subsystem then memory subsystem then returns machine instruction or data at that memory address back to CPU. The program of visible machine state includes the program counter, PC, that holds the address of next instruction to execute, whose name is EIP on 32-bit x86 or RIP on 64-bit x86. And register file, which is a collection of registers. Condition code, which is special registers that store status information about most recent ALU operation, and which is used for conditional branching. And lastly, memory, that includes the stack memory area that is used to support function calls or procedure calls. Let's talk about two types of processors designed with a different philosophy: CISC and RISC. The CISC, complex instruction set computers, use a large number of instructions, varying instruction lengths, and various addressing formats. It requires complex compiler and hardware, but usually generates compact machine code. x86 is a CISC processor. In contrast, the RISC, the reduced instruction set computers, has a smaller number of instructions, fixed instruction lengths, and only a few addressing formats. Therefore, compiler and hardware are simpler, but machine code is usually a bit larger in size. ARM is a good example of RISC machine. Let's take a deeper look at x86 assembly code. This is the same example that we looked at earlier. There are 6 assembly instructions, and each instruction consists of one opcode and 0 or more operands. Opcode is like command, and operands are like arguments. In case of multiple operands, the first one right next to the opcode is source operand, followed by the destination operand. Operand could be registers, memory location, or constant number. Look, the return opcode does not have any operand. The sum in the first line is a label, which is the same as a original C function name. Also, the most opcodes have a size designation suffix L in this example, such as push L, move L, add L, pop L, etc. This size designation suffix indicates the size of operands. For L suffix, it means operands are 4 bytes.